This is section 5.1, Exponential Functions. Okay, so in this section we're going to look at and explore exponential functions. Exponential functions arise in business when we talk about things like the balance in a bank account or a saving instrument, any kind of financial instrument where earnings are reinvested, and that will always result in exponential growth. Okay, definitions. An exponential growth or decay function is a function that grows or shrinks at a constant rate given as a percentage. We often write these functions in this form. F of x is equal to a times quantity 1 plus r raised to the x power. Okay, about these constants in our function. So the only variable in this function is x. A and r are constants. And a is the initial or starting value of the function, like often the value of a bank account at time 0 when you first open the account. Say, and r is the percent growth or decay rate written as a decimal. It's important that we always express the growth or decay rate as a decimal. And then the quantity 1 plus r, we call that the growth factor or the growth multiplier. So the fundamental difference between exponential growth or linear growth is you see that although exponential growth grows more slowly initially, because the growth that already happened causes more growth in the future, it eventually grows more quickly, and eventually you see, like at this point, the exponential growth overtakes the linear growth. Okay, so exponential growth is always denoted, or you always recognize it when you see these graphs that start to blow up and start to grow crazy fast. Okay, let's look at an example. To see the difference between linear growth and exponential growth, consider two companies. So company A has 100 stores and expands by opening 50 new stores each year. Company B has 100 stores and expands by increasing the number of stores by 50% of their total each year. Okay, so this is fundamentally different kinds of growth. So let's see what happens. Looking at a few years of growth for these two companies. So we see here in this leftmost column the year, and then we have the number of stores for company A, and then the far right column is the number of stores for company B. So let's see what happens to store A. Store A is very predictable. At the beginning they have 100 stores. After 1 year they've expanded by 50 new stores, so they have 150 stores. After another year, they expand by another 50 stores. They have 200 stores, so on and so forth. They have 250 stores after 3 years. But what if company B, what happens with company B that expands by a percentage of their total each year, 50% of their total? So at year 0, they have 100, and then 50% of 100 is 50 stores. So after 1 year, they will have 50 new stores for a total of 150. Okay, but the next year, now they're going to add not 50 new stores, but 50% of 150. Half of 150 is 75. So they're going to add 75 new stores to their 150 existing stores, and they'll have 225 stores after 2 years, so more than store company A, right? And then in the third year, they add 50% of 225 for a total of 337 and a half stores. So if you compare these two ending quantities, company A ends with 250 stores after 3 years, whereas company B ends with 37.5 stores after 3 years. So exponential growth can grow much more quickly than linear growth. But it can take a while for that to happen if the growth rate is small. This is a large growth rate. 50% is quite large. Okay, I want to help you see a pattern that's occurring here in the company B's exponential growth. So what happens? So the very first calculation we do is this one right here, right? We do 100 plus 0.5 or 50% times 100 to get the total. Well, we can factor 100 out of both of those terms and rewrite the expression this way as 100 times quantity 1 plus 0.5, right? Okay, so simple enough. Well, after 2 years, what do? We take the current total, 150 stores, and then we add 50% of that. But then we can do the same thing. We can factor 150 out of both of those terms, and we get this expression here, okay? But what can we do to that? Well, recall that the multiplier out front, that 150, it originally came from 100 plus 100 times 1 plus 0.5. So if we replace the 150 in this expression right here with this expression, which is equal to 150, then we get this quantity down below, or this is the key one right here, okay? Now, again, we can continue doing this. And the key idea really is that each time, what are we doing? We're multiplying the previous amount by a factor of 1 plus 0.5 or 1.5. You know, see, that's really the key. Each time what we're doing is we're just multiplying the previous year's value by a factor of 1.5. And so we can summarize after 3 years, what's going to happen is we're going to have 100 times 1.5 to the third power. Okay, notice the exponents on these. I'm going to put a 1 in right here. And notice, so here's an exponent of 1, here's an exponent of 2, exponent of 3. Okay? So in general, if we were to call this, name this function b as a function of n, the number of years, then we would get this expression. So this is the general expression we can use to generate the number of stores for company B after n years. Okay? Okay, so that's the idea of where this, and notice how similar this function is. This b of n is to f of x. Okay? A is 100, the 1 plus r is the 1 plus 0.5, and instead of using n, we're using x in this f function. But it's the same basic function, right? F of x is just a generalization of the b of n function. Okay, so here we have a graph of the growth of company A and company B. Company A is just a linear function, so its graph is a line, but company B's growth is exponential, and you see how much faster company B grows. So one of the takeaways of exponential growth is that it grows, it will eventually overtake any kind of linear or even polynomial growth, okay? And it just, after a while, it will blow up and just get huge. And so it's something you have to be careful about, right? Okay, let's look at an example here. It'll be more similar to your homework. The number of players of a popular smartphone game Candy Crush was initially 11,000. and grows by 5.7% each year. Let P represent the number of players of the game and T the number of years since the game was introduced. Okay, so we're going to write P, think of it like population of Candy Crush players, right? And it'll be a function of time in years. So we want to use this model here to write our function. So basically what we need to do is determine A and R. So the population of Candy Crush players as a function of time, well, initially it's 11,000. So we put the 11,000 out front, and it's growing by 5.7% each year, so we're going to write 1 plus, and we need to always represent percentages as decimal numbers, so 5.7% is 0.057, and we'll raise that to the t power, to the number of years. And typically what we do is we'll rewrite this as 11,000 times 1.057 raised to the t power. Okay. Part B, how many players will the game have in 4 years? So now we want to evaluate this function at t equals 4. And let's switch over to the calculator to do this. 11,000 times 1.057 raised to the 4th power. And since this is people, it makes sense to round to the nearest whole number. So we'll say this is approximately equal to 13,731. Okay. So the number of players will go from 11,000 to 13,000 in 4 years, but it'll continue to grow, and the growth will add on to the previous growth, so it'll start growing much more quickly. How about this exercise? The number of people in a certain region that watch movies on Amazon Prime has an annual growth rate of 12% per year. It is estimated that the number of people that watched movies on Amazon Prime in 2016 was 28,900. How many will watch movies on Amazon Prime in the year 2022? Let t equal 0 correspond to the year 2016. Okay, so we are given the growth rate, 12%, and the initial number of Amazon Prime viewers at 28,900. Okay, so let's see, what is our model? Our model is P of t is equal to 28,900 times 1 plus, now 12% is 0.12, and this will be raised to the t. Now, if I always like to do a little table, let's see here, year and t. Okay, so the year 2016, that's time 0, and then the year 2022, well, that is, let's see, 4 plus 2, 6 years later. So that's going to be a time of, correspond with time equals, or t equals 6. So in order to compute the number of Amazon Prime viewers in the year 22, we need to compute P of 6. So P of 6 is going to equal 28,900 times 1.12 raised to the 6th power. And that is, let's see, 28,900 times 1.12 raised to the 6th power. Looks good. So it looks like, again, we should probably round to the nearest person. 57,043. Okay. Next, a vehicle purchased for $32,500 depreciates at a constant rate of 8% per year. Determine the approximate value of the vehicle 11 years after it was purchased. Okay, so this is going to be instead of exponential growth, it'll be exponential decay. So how do we do decay? Well, we need a name for our function. Let's call it v of t for value. So v of t is going to equal a times 1 plus r raised to the t. Okay, where a is the initial value and r is the growth rate if r is positive, but it'll be a decay rate if r is negative. So because it's depreciating is the opposite of appreciation. So our growth rate is actually negative 8%. So our value function should be the original value of the car, 32,500 times 1 minus 0.08 raised to the t, which simplifies to 32,500 times 0.92 raised to the t. And we want to know the approximate value of the vehicle in 11 years. So then v of 11, that's going to be 32,500 times 0.92 to the 11th power. So let's put that into the calculator. 32,500 times 0.92 raised to the 11th power. That looks good. So we would expect the value of the car, since this is a dollar amount, we'll round to the nearest penny or cent, and we get $12,988.21. Sneak a dollar sign in there. Okay. So notice that the rate is negative, but what gives us exponential decay? We get exponential decay when our base, this is our base, is between 0 and 1. It's not negative. It's a positive number, the base, but it's a number between 0 and 1. And when you have that kind of a multiplier that you multiply by each time period, your values are going to decrease. Okay. A house was valued at $120,000 in the year 1995. The value appreciated to $170,000 by the year 2007. Part A, what was the annual growth rate between 1995 and 2007? Okay, so now we want to determine R, the growth rate. So how can we set this up? Well, let's see, what would be, maybe call the function v of t again for value as a function of time. So the value as a function of time would be, let's see, the starting value was $120,000 times 1 plus r, we don't know the growth rate yet, raised to the t. Okay. And what do we know? We know that in the year 2007, the value appreciated to $170,000. So we know, let's see, 2007, that's 7 plus 5, that's 12 years after 1995. So we know V of 12, right? V of 12 is 170,000. So let's write that out. 170,000 equals 120,000 times 1 plus r raised to the 12th power. Okay, if I divide both sides of this equation by 120,000, I'm going to get, well, I'll write it out. 170,000 divided by 120,000 equals 1 plus r raised to the 12th. And I want to solve this for r. The left-hand side, of course, simplifies to just 17/12. So I have 17/12 equals 1 plus r raised to the 12th power. And how do I undo the raising to the 12th power? I want to isolate r. The way I undo raising to the 12th power is I take a 12th root to both sides of the equation. So I'm going to do a 12th root of 17/12 and a 12th root of that expression on the right. So I get the 12th root of 17/12 is equal to 1 plus r. Kind of think of it as these cancel each other out, right? And so r is going to be equal to, you know what, I can also write 17/12, the 12th root of that, as 17/12 raised to the 1/12 power. And then if I subtract 1 from both sides, I'm going to solve that equation for r. What is this quantity? Let's see here. So parentheses 17 divided by 12 raised to the parentheses 1 divided by 12 power. And I got to get out of the exponent and subtract 1. Okay, that looks good to me. And I'm going to get a rate of about, we want to express this maybe as a percentage. That looks like 2.945%. 2.945%. Okay. So there we go. Assuming house values continue to grow by the same percentage, what will the value of the house be in the year 2012? Let's see, 2012, that's going to be a full 12 plus 5, 17 years after our time zero of 1995. So we want to compute the value when time equals 17. So what is v of 17. Now that we know what r is, we can compute that. And this is going to equal 120,000 times 1.02945. You know, I'm going to use all the digits here, and I'll explain why in just a minute. 09047 raised to the 17th power. Okay, let's do this on the calculator then. Let's see, we're going to get 120,000 times 1 plus, and then I'm just going to go use my calculator and highlight my previous answer, or I could just say answer, either way, and hit enter. Oh, it's not quite what I wanted, is it? I think I hit enter twice accidentally. Yeah, let's just do that again. 120,000 times 1 plus, I'll go highlight that, the rate, hit enter once, there we go, close the parentheses, and raise to the 17th power. There we go. Okay, and so we expect the house, if we round to the nearest penny, we expect the price to be $196,551.84. Okay, now, whenever you're doing exponential problems, they're very sensitive to the growth or decay rate. Thus, if you only use a few digits of precision in your growth or decay rate, well, you might, if we're looking at long periods of time especially, you might get very drastically different results if you say only use 3 digits of precision versus say 5 or 6. Okay, the difference can be kind of large depending on the growth rate. So you want to be careful when doing any kind of exponential functions that you, whenever you can, just use all the digits that your calculator gives you, is my word of advice. Other than that, I would say you probably want to use at least 5 digits or 5 or 6 digits of precision for that growth or decay rate, okay, as a decimal. Okay, so graphical features of exponential functions. First, notice that we can just rewrite our function a times 1 plus r raised to the x power as a times b raised to the x power, where b is just 1 plus r. It's our growth multiplier or growth factor, okay? A few things about exponential functions. Notice for both of these functions, if I evaluate them at x equals 0, then I have my base raised to the 0th power, and any number raised to the 0 power is just going to be 1. And so I'm going to get a times 1 for both of these expressions. Okay, so the point is that every exponential function has a y-intercept at 0, a. Let's see, what else? Number 2 here, b, the base, or the growth factor, determines the rate at which the graph grows. So let's assume just that our starting value is positive. It's a positive number. This is most common. Then the function will increase when our growth factor b is greater than 1. And the function will decrease when b is between 0 and 1. Okay? So that's a key idea to remember, is that this growth multiplier or growth factor b determines the behavior, whether or not you have exponential growth or exponential exponential decay. Okay. Part 3, the graph will have a horizontal asymptote at y equals 0. Okay, so the graph will, so in the first case where we have exponential growth, as x approaches negative infinity, the graph will approach the horizontal asymptote. And in the case of exponential decay, as x goes to positive infinity, the graph will approach that horizontal asymptote, the x-axis, or the line y equals 0. Part 4, the domain of all exponential functions is all real numbers. You can put in any number into an exponential function. But the range is not all numbers. The range of exponential functions is 0 to infinity. Okay. Let's see here. So here we have a couple graphs of functions, of exponential functions with different bases, to give you a feel for how the base determines the behavior of the function. So notice that whenever the base is a number between 0 and 1, so I'm thinking of these functions over here, these functions will correspond with exponential decay, whereas with these functions over on the right-hand side, the base here is a number greater than 1, and so these functions correspond with exponential growth. Another thing to notice is that the greater the base is, the faster the growth. And on the other side, what do we have? We have the closer that the base is to 1, the flatter the graph will get. Or another way to think of it is the closer the base is to 0, the faster the function will decay. Okay? So let's now use that information to do a simple little matching problem here. This would be a good place to pause the video and see if you can figure out which functions, these functions on the left-hand side, which graphs do they match up with? Okay, so pause the video for a moment and give that a try on your own, and then I'll do it with you. Okay, so let's see here. The first thing I notice is that this is my A column here. This is my A, this is my B, and I've got B raised to the x power. Okay? And the A, remember, it gives us our y intercept. So there's only one function that has an A value of 4. And that must correspond with this function right here that has a y-intercept of 4. So this, let's see, p of x, this second function has to be p of x. Okay? Because it's the only one that goes through 4. Now, all the other graphs go through 3. So now we're going to have to use the base to determine which is which. So I see, let's see, F and G are clearly exponential decay functions. So that means their base will be between 0 and 1. So let's see, which functions have a base between 0 and 1. It looks like the first one here and this fourth function here. Okay, so now which is F and which is G? Well, it looks to me like the one that is decaying more rapidly is G. So it's going to have the number that's closer to 0, right? Closer to 0, and that's this one right here. So this is g of x, and this has to be f of x. The other way to think of this, if you prefer, is that the flatter decay function will have the number, the base closer to 1, okay? And 0.7 is closer to 1 than 0.5. Okay, finally we have, let's see, two more functions. We have h of x and r of x, which both go through the point 0, 3. And it looks to me like h of x, it has a greater growth rate than r of x. So of the two remaining functions, the one that's greater, the 1 plus r, the one that has the greater growth factor would be this 1.5. So this has to be h of x, and this has to be r of x. Okay. And there we go. Okay. Let's talk about compound interest. Typically, bank accounts and other savings instruments in which earnings are reinvested, such as mutual funds and retirement accounts, utilize compound interest. The term compounding comes from the fact that interest is earned on not just the original deposit, but on the accumulated value of the account. So you're earning interest on your interest, your previous interest, okay? This causes exponential growth. Okay, so we can compute compound interest using this formula here. Now, you don't need to memorize this formula. I know it's kind of complicated. We'll give this to you on exams, but you definitely need to know how to use it, and you need to know what the different pieces of it refer to. So A of t represents the account value after t years. T is measured in years. And we'll always do years for this kind of problem. Lowercase a is the starting amount of the account, also called the principal. R is the annual percentage rate, but we still need to express it as a decimal value. But it will often be given to us as a percentage. But when we put it in the formula, we need to write it as a decimal. K is the number of compounding periods in 1 year. So K for compounding, right? Okay. So compounding periods, if you had like monthly compounding, you would have K would equal 12. If you had quarterly compounding, K would equal 4 because you're doing a compounding each quarter, which quarter of a year. Let's try this exercise. Compare the following investments. Which has a larger ending balance? Okay, this is a fun little problem to see which one's going to be better. So the first one, Jason invested $9,735 at 9% interest per year in an account that was compounded quarterly for 29 years. And in the second one, we have Alicia set up the same investment as Jason, except she invested twice as much money for half as long. Okay, so, what's better? Investing for a longer period of time, or putting in more money up front, twice as much money, but keeping it in for half as long? Which is more important, the initial deposit or the term of the account? Well, let's compute and see. So it appears that for Jason's account, we'll do A of t is equal to 9,735 times, okay, now remember the formula here. So this is my A I just put in. And now we want 1 plus my interest rate, which is 9%, so I written as a decimal, 0.09, divided by K. Now this was compounded quarterly. So my k is equal to 4. And I want to raise this to the k times t power, so it's going to be 4 times 29, because we're leaving the money in this account for 29 years. All right, let's put this into the calculator. See what we get. 9,735 times 1 plus 0.09 divided by 4. Close parentheses, and then my exponent will be 4 times 29. Okay, that looks good. And we'll always, whenever doing any kind of financial calculations, we'll just round to the nearest penny. So this will be worth $128,000. $128,611.76. Okay, nice. How about Alicia? What formula should we use for her? Well, she's not investing 9,735. She's investing twice that amount, so 2 times 9,735. So she's investing $19,470 initially. But she gets the same interest rate, 0.09%, and she gets the same compounding setup quarterly. But she's not going to keep the money in there for 29 years. She's going to do it for half as long, so 29 divided by 2. So she's going to keep the money in there for 14.5 years. Okay, what is this amount? Let's compute. 19,470 times 1 plus 0.09 divided by 4 raised to the 4 times 14.5. Significantly less. $70,768.23. Okay, so what's the takeaway from this? Time is money. Okay, time is what really builds up your account. Okay, obviously, putting more money in helps as well. Having a better interest rate helps, but if you have a long period of time, you can really see some large returns if you have a constant rate of return. Okay. So what I want to do now here is compare how changing the number of compounding periods, the K, right? How that affects the ending balance of an investment. So how does it change things when you go from, say, quarterly compounding to monthly to, say, maybe weekly, daily, hourly? Okay. So suppose you invest $3,000 in an investment account paying 7.25% interest for 10 years. How much will the account be worth for the following compounding periods? So we've got annual, quarterly, monthly, and daily compounding. Okay. And so I've already done all the calculations here, and we see that if we just do one compounding per year, in other words, annual compounding, K equals 1, the account will be worth $6,040.80 in 10 years. Okay? If we do quarterly compounding, that value jumps to $6,154.11 for a difference of $113.31. So these numbers over here in this column over here, These are the difference between the two values. So we see with monthly compounding, the account grows to $6,180.70. With daily compounding, k equals 365, we get an account balance of $6,193.75. Okay. So, but notice what's happening here is that, yeah, as k increases, the account balance is increasing, but we're getting less and smaller and smaller and smaller increases, even though k is growing quite large. Notice that going from when k went from 4 to 12, we had an increase of about $26.59 in our account. And then when k went from 12 to 365, a huge leap, right? K really grew, but it only amounted to $13.05 more than the monthly compounding. Okay. So, as you might suspect, the number of compounding periods per year is there's a limit to compounding. Okay, so observe that increasing the number of compounding periods increases the amount we earn. However, as k grows, the increase in earnings shrinks, suggesting that there may be a limit to compounding. For example, the increase from annual to quarterly compounding is larger than the increase from monthly to daily compounding. So these facts strongly suggest that although increasing the frequency of compounding will increase earnings, there is an upper limit to this process. Now, so let's really simplify things down as much as possible and just use really simple numbers. So we're going to imagine investing now $1, okay, at a super amazing 100% interest rate for just 1 year, though. And then what we're going to do is, in this column, is we're going to change k. Okay, so k equals 1 in the first row. Semi-annual compounding, k would be 2. Quarterly compounding, k would be 4. Then we go to 12. Monthly, daily would be 365 compoundings. Hourly would be what? Well, hourly would be 24 times per day. So we'd have to do 24 times 365. Okay, I don't know what that number is, but... And then to go to hourly to minutely compounding, we would multiply the previous number by 60. And then to go to compounding every second, we'd multiply that value by 60, and so on and so forth, to get our k values, the number of compoundings per year. Okay, but notice what happens to these values. Yeah, they increase. Okay, they go from 2 to 2 1/4, 2.44, 2.61, 2.71. But notice, once we get to 2.71, it's just the trailing decimals that continue to grow, and your account really isn't increasing by very much at that point anymore, is it? And so the point is that there's this limiting value here where this last column is very close to the limiting value. Okay. Now, this limit value is so important in mathematics that it has its own symbol. Okay, we give this the letter E, the symbol E. Specifically, E is the symbol which represents the value of this expression, 1 plus 1 over k raised to the k power as k approaches infinity. You can try this on your calculator. Try this. Computing with maybe starting with k equals 10, and then go to 20, then 50, then 100, then 1,000, then 1,000,000 or something like that. And you'll see that, yeah, indeed, as you take larger and larger values of k, in other words, as k approaches infinity, this is going to get closer and closer and closer to the number 2.7182818 or something like that. Yeah, this number right here. Okay. So E is a number that's very important in mathematics, kind of like pi. Just like pi, it's also an irrational number. You can't express E as a ratio of two integers. But the importance of E is that it allows us to go from growth that happens on a frequent basis, like with compounding, with K, to continuous growth. So the growth is happening continuously, okay? And it also gives us this new function, f of x equals e to the x, which is a very important function in calculus, especially. But it's not an exaggeration to say that this exponential function is used throughout the sciences and engineering, economics, you name it. This comes up all the time if you go further into mathematics. Okay. The way we usually use this exponential function with this new base of e is this formula right here. So if we want to model continuous growth or continuous decay, we can do this, use this function f of t is equal to a times e to the rt, where a is the starting amount, r is the continuous growth rate or decay rate, and t is time. You can kind of think of it like this, as when we have discrete growth, in the discrete case, where we have a discrete number of compounding periods per year, we have b is equal to this 1 plus r over k raised to the k power, right? Well, in the case of continuous growth, you should think of it as our base is this e to the r, okay? So it's just a different way of thinking about growth. And the important idea is that the base you use is not terribly important, we'll see, okay? But that's kind of more for an advanced class for calculus or something. Okay, so while continuous compounding is not typically used for savings accounts, it is used heavily in the world of finance to model financial instruments which do change continuously, such as stocks. In the natural world, there are many things which change continuously or nearly so. For example, chemical reactions, bacterial populations, and radioactive decay are just a couple of examples. So let's see here. Suppose a colony of bacteria initially has 20,000 bacteria which reproduce continuously. If the population is observed to grow by 4.4% per day, what size will the population be after 25 days? So, I'm going to show you two ways to approach this problem. First is kind of just the brute force, straightforward way of thinking about it. First, I'm going to write down the model. Our model is, we're told that these bacteria reproduce continuously. So we want to use continuous exponential growth, or this model up above. So I'm going to, instead of calling it f of t, I'm going to call it p of t for population of bacteria, right? What is our population size? So p of t is going to equal a times e to the rt. Okay. Where a is the starting amount, so in this case we start with 20,000 bacteria. And then you might be tempted to put in 4.4 as or 0.044 as r, but that wouldn't be quite right. I know you'll see why in just a moment, but this is our model. There's our model. And now we're going to use this model to figure out what r is. Okay, and we'll see it's not quite 4.4. It's a little less. Okay, so how do we figure out r? Well, if they grow at a rate of 4.4% per day, that means that we're going to have, on day 2, we're going to have, let's see, 20,000, right, times 1 plus 0.044, okay? So this is how many bacteria we should have on day 2 if the population is observed to grow by 4.4% per day. So what is this amount? It's 20,880 bacteria on day 2. Okay, so then now we know this. We know this fact that P of 2, this is equal to 20,000, or sorry, this should be, sorry, this is P of 1. This is after 1 day, sorry. P of 1 is going to equal 20,880, which is equal to our 20,000 times e to the r times 1, because it's 1 day. Now, everything in that equation is known except for r. So we can solve for r and get the correct growth rate to use for continuous growth. So I'm going to divide both sides of the equation by 20,000. Okay. And let's see. Well, we kind of need to jump the gun here, and this is a great introduction for what we're going to be doing in the next lesson. But to solve this, we need to be able to undo exponentiation base e, and the way to do this is to take a logarithm of both sides. Okay, and we want to use a logarithm base e. So we'll learn all about this next time, so if you don't understand this function at all, that's okay. But to solve for r, we do need to take a logarithm of both sides of this equation. Let's see, so we're going to get, and this over here, 20,880, let's simplify that. 20,880 divided by 20,000 is what? So it's 1.044. Okay. So I get 1.044 equals e to the r. Okay, now I'm going to take what's called the natural logarithm of both sides of the equation, 1.044. And the key idea is that when we take the natural logarithm of an exponential, we'll see this in the next lesson, but it allows us to rewrite this as r times the natural log of e, and this is just 1. The natural log of e is 1. So we get that r equals the natural log of 1.044, which is about, let's see, we use this ln button for natural logarithm, 1.044. Notice it's a little less than 4.4%. It's about 0.0 0, 4, 3, 0, 5, 9, 4, 8, 9, 5. I'm going to write out all the digits again because we need to be careful when doing exponentials and not truncate our growth rate too much, too aggressively. Okay. So there's our growth rate. Now we can actually compute what the size of the population will be after 25 days. So let's see. So P of 25 will equal 20,000 times e to the, and you know, I'm not going to write that big long decimal number. I'm just going to write r times 25. Okay. Let's compute this on the calculator. So let's see here. I have 20,000 times e to the x. That's this button on my calculator, this e to the x button. And I'm going to just go fetch that value for r. Let's see here. In fact, I'm going to use this function, the exact value right here instead of an approximation. And then I'm going to multiply that times 25. Okay, and now let's see, get out of the exponent. That looks good to me. What do we get? We get a population of 58,687 bacteria if we round to the nearest bacteria. So we'll put a little, and maybe we should label that with bacteria. Okay. And this concludes section 5.1 on exponential functions.